Hi everyone, welcome back to another video. So in this video I'm going to start studying my Instrumentation and Control module for university. Although it's not part of my plan to start studying this one yet, and I should be doing other stuff. I don't know if you saw my last video where I said that I wanted to focus on maths. I'm just kind of eager to get started with the Instrumentation and Control side of things. And that's the thing about plans and schedules. You're not tyrants, you don't have to stick to them or anything. So I'm I feel motivated to start learning instrumentation and control, so therefore I'm gonna do it. And that's honestly the way that you should go about it. It's easier for you to go with where you feel motivated. So I'm gonna get started with instrumentation and control. So when I'm studying, there's two things that I do. The first thing is take the books that I need to be learning, and I skim through them, and I just get an idea of what the topic's about. Even though obviously I've already kind of done that in terms of the table of contents of the book. Now I'm actually looking to go through the whole book, skim through the whole book, get through it in half an hour, and just have way more of an idea of what the topic's actually on. Some of the things that I'll do is, you'll see in this video, I'll take a paragraph and I'll just read half a sentence or a sentence of that paragraph, and I'll carry on. I'll just skip to the next paragraph, and it just gives me a really nice feel for what the subject's about, even more so than what we've already done here as well. So let's go and open up our folder on Dropbox, Instrumentation and Control. And then so we've downloaded a fair amount of books here. So we've got the 2 for instrumentation, we've got 3 for control, and 3 for PLC programming. So assume we're gonna go for Mechatronics, electronic control systems in mechanical and electrical engineering 6th edition, or DG aspirants mechatronics. So let's go for this one. Yeah, this is the book that I really wanted to go through. Just looking at the cover, it motivates me. I want to read it. Alright, so what I'm gonna do is we're gonna swing through this whole book. So how many pages we got? We've got 663 pages. So we're gonna swing through the whole book, and we are going to skim through it and take some notes on it as well. So let's do this. We're going to create a page here in Notion for where I should put. Let's make a page and we'll call it, what should we call the page? Let's call it notes on Mechatronics W Bolton. Start with the introduction. We'll take a quick look at the preface actually. The term mechatronics was invented by a Japanese engineer in 1969 as a combination of mecha from mechanisms and tronics from electronics. The word now has a wider meaning, being used to describe a philosophy in engineering technology in which there is a coordinated, currently developed integration of mechanical engineering with electronics and intelligent computer control in the design and manufacture of products and processes. As a result, many products which used have mechanical functions have had many replaced with ones involving microprocessors. Yep. That's true. This has resulted in much greater flexibility, easier redesign and reprogramming. Yep. And the ability to carry out automated data collection and reporting. Yep. Because obviously you're no longer servicing machines and parts, you're just upgrading software. A consequence of this approach is the need for engineers and technicians to adopt an interdisciplinary and integrated approach to engineering. Yep. Thus, engineers and technicians need skills and knowledge that are not confined to a single subject area. Yep. They need to be capable of operating and communicating across a range of engineering disciplines and linking with those having more specialized skills. This book is an attempt to provide a basic background to mechatronics and provide links through to more specialized skills. First edition was designed to cover the Business and Technology Education Council, that's what I said for, Mechatronics unit, for higher national certificate diploma courses for technicians, and designed to fit alongside more specialist units such as those for design, manufacture, and maintenance, determined by the application area of the course. Okay, the book was widely used for such courses and also found used in undergraduate courses in both Britain and the US. Following feedback from lecturers in both Britain and the US, the second edition was considerably extended. So, okay, it's just going on about the book and how it's extended. Also objectives, key points summaries were included with each. Okay, that's fine. 6th edition, which is what we're on now. The new edition has involved moving the system modules part so that it comes after micro. Okay, so it's just talking about different adjustments. Fine. Alright, so let's get started. Part 1. Okay, so introducing mechatronics. The objectives of this chapter are, after studying it, the reader should be able to explain what is meant by mechatronics and appreciate its relevance. What is meant by system-defined elements. Okay. So the term mechatronics was invented, as we've already said. That's fine. Okay, read that. Marriage of electrical and mechanical systems and its modern control system. It's complete integration of all of them. Current approach to design. Okay. In design of cars, robots, machine tools, blah blah blah. Integration, such an integrating interdisciplinary approach to engineering design is increasingly being adopted. Okay. So the basic elements of a mechatronic system. Alright, so take this. Basic elements. Right. Remember, I'm just keeping in mind that the subject is instrumentation and control, and we're talking about the basic elements of a mechatronic system, which are, you've got a microprocessor system for control, you've got a mechanical system, and between them you've got actuators and sensors. Yeah, that makes sense to me. Okay, so consider the modern autofocus auto exposure camera. All right, to use the camera, all you need to do is point it at the subject and press the button to take the picture. The camera can automatically adjust the focus. That's actually true, you know. I didn't actually even consider that. Obviously it's a software thing that it's doing. The camera can automatically adjust the focus so that the subject is in focus and automatically adjust the aperture and shutter speed. Yep. Okay. Consider truck smart suspension. Such as suspension adjusts to uneven loading to maintain a level platform. Yeah. You know, this is what I love about engineering. You know, sometimes I'm at a traffic light and I look at it and I'm seeing the, you know, sometimes you go to traffic light in the day and then you go back at night time and it runs at a complete different speed and you're thinking, oh, there's obviously some sort of timing algorithm to this. Automated production line. Such a line may involve a number of production processes which are all automatically carried out in the correct sequence and in the correct way. Okay, so basically giving you examples there. Embedded systems. The term embedded system is used when microprocessors are embedded into systems, and it is this type of a system we are generally concerned with in mechatronics. What? Okay, the term embedded system is used. Yeah, you put a microprocessor in something into a system. Yep. And it is a type of system where we are generally concerned with in mechatronics. Okay. A microprocessor may be considered as being essentially a collection of logic gates. Yep, I don't know what that is. AND gates, OR gates. Yep, that's fine. For microprocessor to be used in a control system, it needs additional chips. Microcontrollers are microprocessors with these extra facilities. Yep, this is what we know this stuff from last year. Okay, design process for any system can be considered as involving a number of stages. Right, the design process. This is just the engineering design process. Similar. So what are we talking about here? The need, analysis of problem, preparation of specification, generation of possible solutions, selection of suitable solutions, production. Okay, that's fine. Traditional and mechatronics designs. Engineering design is a complex process involving interactions between many skills and disciplines. This is the introduction, right? So it's very, very wordy. So what's talking about LEDs here? For example, springs might be replaced by load cells with strain gauges, and the output from them used with a microprocessor to provide a digital readout of the weight of the thiamine diode. Okay, so that's bathroom scales, right? In designing mechatronic systems, one of the steps involved is the creation of a model of the system so that predictions can be made regarding its behavior when inputs occur. Such models involve drawing block diagrams to represent systems. The system can be thought of as a box or block diagram, which has an input and an output, and where we are concerned not with what goes on inside the box, but with only the relationship between the output and the input. Yep, I'm cool with that. Input force, output extension, input electric power, output rotation. input temperature, output number, and scale. Yeah, yeah, it's yeah, good way. It's like the whole black box thing. Okay. Term modeling is used when we represent the behavior. Okay, that's modeling. Yep. The response of any system to an input is not instantaneous. Yep. True. But that may feel like that. For example, okay. The responsive systems are functions of time. Thus, in order to know how systems behave when there are inputs to them, we need to devise models for systems which relate the output to the input, so we can work out for a given input how the output will vary with time and what it will settle down to. Okay, so as another example, if you switch on a kettle, it takes some time for the water in the kettle to reach boiling point. Likewise, when a microprocessor controller gives a signal to say move the lens for focusing in an automatic camera, then it takes time before the lens reaches its position for correct focusing. Often, the relationship between the input and output for a system is described by a differential equation. Oh dear, this is this is where the maths comes in, huh? I'm gonna cry already. We're in the introduction, and you're talking about differential equations. Okay, cool. Okay, such equation systems are discussed in chapter 17. Thank you, chapter 17. I thank you not for not being in chapter 1. Okay, so I'd like to just. This is the first time I've ever really thought about something like this. It's never occurred to me. So I'd like to take some sort of notes on it. Let's just. The response to any system is not instantaneous. It's a different modeling system. Responsive system function of time. Okay, I'll take some time. Boiling point. Camera. Okay, now what I'm gonna do is instead of I don't want it to be text heavy. Too much text puts me off. So let's go with. I'll remember that. So system response time. Basic element. The purpose of me taking notes is it's more of just a way of kind of absorbing the information, and I'm not really gonna go back to these notes other than just as a way of refreshing what the book spoke about. Right. So in order to connect system, in other than the simplest systems, it's generally useful to consider it as a series of interconnected blocks. Each such block having a specific function. We then have the output from one block becoming the input to the next block in the system. You run the system this way, so creating system in terms of blocks. Okay. So you have like, okay, so here's a system. The important point. Connected systems. Consider the system as a series of connected blocks. There's all these shortcuts with Notion that you can use as well to make your workflow much quicker, which I really like as well. And so you can get like that. So what's this? So digital thermometer, a measurement system, and it's quantity being measured. I actually do this myself whenever I'm designing stuff. It's block that I really like block diagrams. Okay, so a control system can be thought of as a system which can be used to control some variable to some particular value, control the sequences of events, control whether an event occurs or not. Okay, so this is like the control side of things, which is not really instrumentation, right? But let's just write down anyways, control system. Okay, so let's do, you can put a numbered list. Yep. Let's do control a variable to value. Alright, and do control the sequence of events. Okay, feedback. Consider an example of a control system with which we are all individually involved. Okay, the body temperature, unless you are ill, remains almost constant regardless of whether you are in a cold or hot environment. To maintain this constancy, your body has a temperature control system. If your temperature begins to increase above the normal level, you sweat. If it decreases, you shiver. Both the mechanisms, temperature, okay, like feedback loop. Yeah, right, feedback. Um, the control system is maintaining constancy over temperature. The system has control system. Yeah, in order to obtain the required temperature. This is an example of feedback control. Feedback control. Signals are fed back from the output, i.e. the actual temperature, in order to modify the reaction. Okay, so let's just, okay, so the control system is maintaining constancy of temperature. The system has an input from sensors which tell it what the temperature is, and then compare this data with what the temperature should be, and then provide the appropriate response in order to obtain the required temperature. Right? Okay, I'm okay with that as well. I feel like this is more robotics kind of stuff, but it's not really, because in terms of electrical engineering, I'm sure you're going to be dealing with a lot of systems. I think of this kind of stuff in terms of robotics, especially when they give you real human examples as well. Okay, open and closed loop systems. There are two basic forms of control systems, one being called the open loop and the other being closed. Okay, I don't know the difference, but it's going to tell me. The difference between these can be illustrated by a simple example. Consider an electric fire which has a selection switch which allows 1 kilowatt or 2 kilowatt heating element to be selected. If a person used the heating element to heat a room, he or she might just switch on the 1 kilowatt element if the room is not required to be at too high a temperature. The room will heat up and reach a temperature which is only determined by the fact that the 1 kilowatt element has switched on, not 2 kilowatt. If they're changing conditions, perhaps someone opened the window, there is no way to heat. Okay, yeah, that's true. Yeah, heat just goes out the window. This is an example of open loop control in that there is no information fed back to the element to adjust it and maintain a constant temperature. Okay, interesting, yeah. So that's an example of open, right? Or yeah, open, yeah. Okay, so open loop versus closed loop. I don't know about you, but this is probably the most that I've learned in the last month. So you can see, like, you know, I don't know if my lecture is going to cover any of this, but when he does cover it, and when he says, "Oh, there's two types of two types of control systems," do you know what they are? And it has to say open loop, and closed loop. People can start thinking, I've studied this before. This guy's going to kill it. He's probably going to get it first again, and it just has to do with I don't know how much have I really read. As you've seen, I'm on page 11 or page 24, and I just skipped. I skip a whole bunch. This is why I do this. It's, like I said as well, it gives you, the main thing is it gives you confidence. It gives you confidence that, what, this stuff isn't too complicated. I understand it. So yeah, I'm happy with that. All right, so two basic forms of a control system, one being open loop and the other closed loop. So we're looking for a basic definition of that, just to remember. So there is no information fed back to element to adjust, maintain. Let's do that. So open. So let's put no information fed back to element to adjust it, and adjust for adjusting, maintaining. Okay. So let's see where it tools closed. Okay. The heating system with the heating element could be made a closed loop system if the person has a thermometer, switches the 1 kilowatt and 2 kilowatt elements on and off according to the difference between the actual temperature and the required temperature. To maintain the temperature at the constant room. In this situation, there is feedback. Input to the system being adjusted according to whether the output is the required. Okay, so closed, and so there is feedback. The input to the system being adjusted according to whether its output is how can you phrase that? Whether its output is met, whether its required output is met. Required output is met. I want to try and write it in terms of general and not specific to a heating, or just specific to the example that they're giving. Okay, so input. So are we looking at, okay? So this is an example of an open loop system. So switches on the heater, hand activated switch, okay, electric power, and then the fire turns on and the temperature changes up or down. Comparison element, required temperature, deviation signal, okay, controller, like the person turns on the switch, okay, then the electric power heats up, get a constant temperature, and then there's a measuring device. But I don't get that, because then it goes back. Why does the controller here? I mean, shouldn't the person be over here? Yeah, I don't get that, but I get the concept anyway. So let's just stick it in. Wait, let's just get the figure part in as well. Okay, alright, that's that. Alright, so basic elements of a closed loop system: comparison element, control element. Okay, so this is where they explain it: correction element, process element, and measurement element. Okay, let's put basic elements of a closed loop system. Comparison element, control element, correction element. So these things, they kind of speak for themselves, don't they? Process element. So what I'll do is on my the morning of my first lecture for instrumentation and control, I'll just go over these notes again, and I won't need to have a look at the book or anything. Alright, so that's the basic elements of a closed loop system. Okay. There's nothing about open loop, analog and digital control system. Okay. Analog systems are ones where all the signals are continuous functions of time, so just real signals. Yep. Digital signals can be considered to be a sequence of on-off signals, the value of the variable being represented by the on-off pulses. So, although I know that already, I don't know if I need to take any notes on it, but let's just do it anyways. Maybe sometimes or oftentimes what happens is, you'll get, I don't know, either weekly reports or something like that, where the lecturer will give you an assignment of some sorts and tell you to discuss what's the difference between analog and digital. And the thing that everyone does is everyone just goes onto Google and just copy and paste something. But when you've got a real example from the book, then on top of that, you can reference it and stick it in your references as well. You're flying. Like that's how you kill reports, because then the lecturer sees that you've actually read the book and you're quoting books, especially if the book isn't searchable on Google, meaning that, so if Google can't actually read this book and put it on its search results, so let's try it, right? So we'll take this, let's search it in Google, see what happens. Yeah, so you see, look, so for example, this one here is searchable. You can see that obviously it comes up straight away. So it's possible for someone, for example, someone in your class to copy and paste this same definition as well. So if you did that, you might get caught for plagiarism or whatever. But there's a lot of books that aren't searchable. So it's always good if you can have like an actual reference. That's going to serve you well. Okay, so, and it is the size of the signal which is a measure of the variable. And I don't get that. And it is the size of the signal which is a measure of the variable. Okay, so what's this one saying? The value of the variable being represented by a sequence of on-off. Yeah. Yeah. I got up early this morning, so I'm not understanding that, but that's okay. Cool, that's fine. Yeah. You see, once I get the gist of I'm just basically reading like the first paragraph of each subsection of the chapters, and there's no need for me to go through all of this. That's what I'm gonna do when I'm actually studying it. But for now, I'm just trying to get a good overview of the subject. So, sequential controllers. There are many situations where control is exercised by items being switched on or off at particular preset times or values in order to control processes and give a step sequence of operations. Step 1 is complete and step 2 starts. Step 2 is complete. Okay. The term sequential control is used when control is such that actions are strictly ordered. Okay. Yeah. Okay. An event-driven sequence. Such control could be attained by an electric circuit with sets of relays or cam-operated switches, which are wired up in such a way as to give the required sequence. Interesting. I just still don't. I've been meaning to get into relays all summer, and I didn't do it, which I'm not happy about. So let's just shorten. You want your notes to be as short as possible. When control, because obviously the book, they're gonna make it make sense in English, but you're not bothered about it making sense in English as long as you can understand. When control is such that actions are when actions when control actions strictly ordered in a time or event driven. Actions and control actions. Such control could be obtained by an electric circuit. Yeah. Okay. Such hardwired circuits are now more likely to have been replaced by a microprocessor control system, which can be controlled by means of software program. Interesting. Okay. Now these hardware electrical systems are replaced by software. Yep. This is a washing machine system. What kind of mentioned here? Integration of sequential control considered domestic washing machine. A number of operations carried out in correct sequence. Okay. Clock, control unit, pump, valve, heater, motor. Okay. That's too much for my brain right now. Programmable logic controller. Program press A. Okay, that's fine. Example of mechatronic systems. Mechatronics bring together technology of sensors, measurement systems, okay, digital camera and autofocus, that's fine. Engine management system. MEMS. What's MEMS? Micro electromechanical system. MEMS are mechanical devices that are built onto semiconductor chips, generally ranging in size, so tiny. They usually consist of microprocessors and components such as microsensors and microactuators. MEMS can sense, control, and activate mechanical processes on the micro scale. Such MEMS chips are becoming increasingly widely used following this illustration. This is an airbag control system. Deceleration, meaning you've hit something. Engine capacitance, signals suitable for actuation, motor activated, airbag deployed. That's cool. Okay, so let's do this. MEMS are mechanical devices that are built on semiconductor chips. Are tiny. Not Tony, tiny. When I'm going over my notes, I don't want to see 20 micrometers to a millimeter. I don't want to see that. I just let me know it's tiny. When I'm actually studying this, in a deep level, then fine. I'll try and learn and get an idea for the fact that it's 0.001 millimeters. They consist of microprocessors and components such as they sense, control, and activate mechanical processes. Microscale. Such MEMS chips are recently widely. So let's just put becoming very popular. Yeah. Okay. So we've got like a summary. This is cool as well because one thing you could do is you could just read over the summary of each chapter. They got some problems for you. That's nice as well. Okay. All right. So as I progress through the book, the thing that I'm going to do is I'm going to speed up my skimming because without a doubt, as you get through the book, remember you've just skimmed through 80% of chapter 1. So there's a lot of stuff that would have been explained that you're not ready to understand yet. So when you get to chapter 2, a lot of it's going to be based upon chapter 1, and so you're just not going to be ready to understand it. So as you see that happening, just skim faster through. That's what I do. So I take I usually take like 20-30 minutes with chapter 1, then I take maybe 15 minutes chapter 2, chapter 3 maybe 10, and then just go down like that to 5, 3, and then usually the last chapter I just fling through it really quickly because, like I said, I've mentioned in the last video as well, usually for your university textbooks, you're not going to be assessed on the last chapters at all. Usually that's like further reading or stuff that would be taught at a much higher level. So yeah, so let's get through this one. So we've got sensors and transducers, which we've kind of touched on in my first year. So the term sensor is used for an element which produces a signal relating to the quantity being measured. And then where's transducer? The term transducer is often used in place of the term sensor. Transducers are defined as elements that, when subject to some physical change, experience a related change. Yep. Okay, I'm okay with that. So let's do, and here sensors and transducers. Transducers. Okay. Cool. Smart sensors. Some sensors come combined with their signal conditioning all in the same package. Such an integrated sensor does still, however, require further data processing. However, it is possible to have the sensor and signal conditioning combined with microprocessor all in the same package. Such an arrangement is termed as a smart sensor. Okay. Let's go smart sensor. Put this bit in bold. Copy that bit there. Here. The one thing I advise you against doing is copy and pasting in a big chunk of text like this. Try and, as you see me do here, try and break it up into a easily readable and understandable thing for you later on. So you can get rid of words like however and stuff like that. So some sensors combined as sensors combined with their signal conditioning, all in the same package. All in the same package. Combined with a microprocessor. Are termed smart sensors. Yeah, there you go. So that big chunk of text into that. Okay, so performance terminology. The following terms are used to define the performance of transducers and often measurement systems as a whole. Okay, so terms used to define performance of transducers and measurement systems. Cool. Terms used to define performance of transducers and measurement systems. Used to define performance. Terms to define. There you go. Okay. Range and span. I kind of have an idea of what that is. Again, have an idea of error. Kind of touched on these things last year. What seems to be good is that it seems like I'm building this year. Oh dear, man. Let me write accuracy. I seem to be building upon what was studied last year, which is nice. I hope it is the case. The thing at the moment is I don't have any of my lectures released, so I could be completely wrong, but you hope that since the lecturer put that this is essential reading, hopefully it's going to be fairly accurate. And from my experience, I did this in my first year as well, and it was bang on, like literally bang on. Everything that I covered in the books was taught in the lessons as well. So deadband time and resolution. I seem to have a problem trying to copy and paste this stuff in. Output impedance. A lot of terms here, right? And yeah, so static and dynamic characteristics. The static characteristics are the values given when steady state conditions occur. What? Steady state conditions occur, i.e. the values given when the transducer has settled down. Okay. So when nothing's going on, what values are received? And the dynamic characteristics are when stuff's going on. Refer to the behavior between the time that the input value changes, time that the value given by transducer settles down to steady state. What? So let me read that again because I didn't understand that. The static characteristics are the values given when steady state conditions occur, i.e. the values given when the transducer has settled down after having received some input. The terminology defined above refers to such a state. Dynamic characteristics refer to the behavior between the time that the input value changes and the time that the value given by the transducer settles down to the steady state value. Dynamic characteristics are stated in terms of the response of the transducer to input in particular forms. Okay, I don't understand that. My only thinking now is I didn't understand that. Should I write it down or not? I think it's personal preference. If you don't understand what you just read, should you be writing it down? Yeah, maybe you'll get it later. I don't know. This is a tricky one for me. I don't know what to do here. Because I don't even know how I would write that down. I mean, what, there's two types of characteristics. Characteristics of what? Of sensors and transducers and stuff? Like measurement systems? What? Okay, so what was the last thing we went through? We went through terms to define performance of transducers and measurement systems. And then now we're on to characteristics. The characteristics of sensors, I assume, are the value given when steady state conditions occur, i.e. the value given when the transducer has settled down after having received some input. And then the dynamic one, okay, so the transducer has received some input and it's settled down. Okay, and the dynamic characteristic is when is referred to the behavior between the time, okay, so between the time that the input value changes, okay, so temperature's gone up, and the time that the value given by the transducer settles down. So it changes, okay, so that small period you assume whereby the temperature's increased but it hasn't settled yet, so it's not fully accurate, I'm guessing. So I'm gonna write this down, but it's gonna be just a you know, a basic copy and paste kind of job here because I don't really get that at all. So dynamic. One thing, I mean, I don't know if you'll be watching this and not having watched the beginning part of this, but I haven't studied this subject yet. I'm just skimming through, so I don't understand what I'm reading here. And this is what I was saying about how I mentioned it maybe 5-10 minutes ago that as you progress through the book, you start to understand less and less. So yeah, just expect it. It happens. You're obviously skimming through, so all right. Okay. All right, is what it is. We carry on. I'm not going to bother with this stuff because I didn't even understand the basic overview. Placement, position, and proximity. Placement sensors are concerned with the measurement of the amount by which some object has been moved, right? I.e. displaced. Yep. Position sensors are concerned with the determination of the position of some object in relation to some reference point. Proximity sensors are a form of position sensor and are used to determine when an object has moved to within some particular critical distance sensor. Interesting, yeah. I'm okay with all of that. proximity, and then where's the other one? Position. Cool. Yep, I'm alright with that. Potentiometer sensor. A potentiometer consists of a resistance element with a sliding contact which can be moved over the length of the element. Such elements can be used for linear or rotary displacements, the displacement being converted into potential difference. Okay, the rotary potentiometer consists of a circular wire and alright, so what's your purpose? I didn't understand how that was a sensor though. I get what a potentiometer is, but where's the sensor part of it? Okay, so you can see we're in the weeds now. Okay, potentiometers are used as sensors. Alright, here we go. With the electronic systems in cars being used for such things as the accelerator pedal position and throttle position. Okay, I don't understand how that works. That's fine. I'm gonna skip strain gauges as well. Kind of cover that in last year. Capacitive element. That's fine. Let's carry on going. Differential transformers. Yeah. The two things. Either my brain is tired, which is a possibility, or I'm just not at this level yet in my knowledge. Like there's too many words here that I don't intuitively understand. When you kind of start to realize that, that's when it's nice. It gives you a good idea of what you don't know and really what you need to be working on. All right, so inductive proximity switch. So this consists of a coil wound around the core. When the end of the coil is close to a metal object, its inductance changes. This change can be monitored by its effect on a resonant circuit, and the change uses a trigger switch. It can only be used for the detection of metal objects and is best with ferrous metals. So they're just basically going through different types of sensors here. So I'm going to skip all of these. All effect, because some of them I've covered in my data acquisition module. So, and then for me personally, the way that I would learn this is, before I read, so for example, before I read any of this, I need to know what it looks like. If you start telling me about a car, I want to know. Let me see first a picture of a car before you start teaching me how a car works. You know what I mean? Like if you're gonna tell me about an engine, I want to know. I want to know what the engine looks like. So, I just tried to click on the video. Why didn't it show me the video? Yeah. Nope. Bloody hell. Take me to YouTube, man. Power electric sensors. So this is what I would do, even though this is great. These videos don't look great. But yeah, this is what I would do. I would get a good idea of Big Clive. This is the guy if you want to learn stuff actually. Yeah. Alright, cool. So let's carry on. There was something forced there, spring. Yeah, that's fine. Still on just sensors, piezoelectric sensor. So yeah, I've covered some of these. Temperature. Still. So it's like basically giving you this kind of subheading, temperature, and it mentions the different types of sensors that are part of the temperature. Light sensors, same. So it's just doing, okay, so you got temperature, pressure, force, light, and then it's just mentioning the different types of sensors that you have. In selecting a sensor for a particular application, there are a number of factors that need to be considered. The nature of the measurement required, obviously. You're not going to use a weighing scale to measure the temperature. The nature of the output required from sensor. nature of the output required. Yep. And then possible sensors can be identified, taking into account such factors as their range. Okay. So I don't know how important this is, but it seems like a good bit of information. So how to select like your nature of the measurement required, nature of the output required from the sensor, and identifying sensor whilst taking into account such factors. To take, consider factors in image action, speed, etc. There you go. Okay, so input and data by switches. Mechanical switches consist of one or more pairs of contacts. Yep, of course, we know that. Term limit switches used when the switches are open or closed. Yep. Mechanical switches are specified in terms of their number of poles. Yep. Single throw, double throw. SPDT, DPDT. Yep. So we know that already. Debouncing, we know the problem debouncing. So I don't know if we would cover this level of sensors in this topic. I don't know. We touched on it in last year's module of data acquisition, so we may or may not go into this level of sensors. I don't know. There was a few sensors there that I haven't heard of. Alright, so signal conditioning. So this is kind of like becoming this again. Signal conditioning was part of data acquisition, so I don't know if we'd cover this in this video or in this. I don't know if we'll cover this in this semester, so we'll see. So signal conditioning, the output signal from the sensor of a measurement system has generally to be processed. Has generally to be processed in some way to make it suitable for the next stage of the operation. Signal may be, for example, too small, have to be amplified, etc. Okay. All these changes can be referred to signal conditioning. Okay, yeah. So I know this stuff already. So signal conditioning processes, section. Getting signal into the right type of signal. So let's put oh dear. Okay, there we go. Getting the level of the signal. Okay, signal, yeah. That's the level of sight. Eliminating or reducing noise. Yeah. Signal manipulation. Yeah. So the op amp. An amplifier can be considered to be essentially a system which has an input and output, the voltage gain of the amplifier being the ratio of the output and input voltages when each is measured relative to the earth. Input impedance of an amplifier is defined as the input voltage divided by the input current, the output impedance being the output voltage divided by the output current. So just cover that generally speaking. The op amp. And let's just put amplifier can be considered to be essentially a system. There's an input and output. voltage gain in the amplifier ratio. Okay. So input voltage, input current, amplifier. Okay. Faster. Alright, inverting amplifier, that's fine. So inverting amplifier shows the connections made to the amplifier when used as an inverting amplifier. The input is taken to the inverting input through a resistor, with the non-inverting input being connected to ground. Okay, let's do that. Non-inverting amplifier again shows the operation amplifier connected as a non-inverting amplifier. The output can be like voltage divider and stuff. Yep. Okay. So I mean, at the moment, I don't understand this stuff, but it's one of those things where I feel like, based upon what I learned last year with voltage dividers, if I read through it, I'd probably get it. And so, I'm definitely not, when I'm skimming, I'm not about to do any maths. Like, anything beyond simple addition, I'm not doing it. Alright, so logarithmic amplifier. Some sensors have outputs which are non-linear. For example, the output from a thermocouple is not a perfectly linear function of a temperature difference between its junctions. A signal conditioner might then be used to linearize the output from such a sensor. This can be done using an operational amplifier circuit, which is designed to have a non-linear relationship between its input and output, so that when its input is non-linear, the output is linear. This is achieved by a suitable choice of component for the feedback loop. Okay, that's fine. We'll just okay. Let's just mention what the logarithmic amplifier does. It'd still be nice to kind of have an idea. Okay. So some sensors have outputs that are non-linear, and then signal condition might then be used to linearize the output. This can be done. So used to linearize the output for such sensor. This can be done using op amplifier circuit, which is designed to have non-linear. Which is designed so that when its input is non-linear, the output is linear. This is achieved by a suitable choice. Okay, so and then we've got a picture of a logarithmic by there. Right. Comparator. Definitely want that. Comparator indicates which of the two voltages is the larger. An operation amplifier uses no feedback or other components can be used as a comparator. Nice. Nice and simple. But I love it. Okay. Oh, where are we going? Why are you embedding temperature switch circuit? Real amplifiers. Operation amplifiers are not in the real world the perfect ideal element discussed in the previous section of a particular significant problem is that of the offset voltage. Okay. We'll just mention that. Oops. Are not in the real world perfect ideal element. A particular significant problem is that of the offset voltage. Okay, so let's just kind of get Definition for offset voltage. So this is known as offset voltage. The output voltage can be made zero by applying a suitable voltage between the input. Okay, I'm gonna get rid of this because when I go back over my notes, there's no way I'm gonna understand that. So protection. There are many situations where the connection of a sensor to the next unit can lead to possible damage as a result of perhaps high current or high voltage. A high current can be protected against by the incorporation input lines of a series resistor, and a fuse break. Yep. High voltage and wrong lines may be protected against by the use of a Zener diode. Yep. Bent backward voltage and stuff. This allows much. Yep. Got that. This is also because Zener diode. Yep. Okay. So up to here. For protection. Okay, so high current. Okay, so there are many situations, connection of sensor next unit. Okay, leave that as that. I'm right with that. Okay, yep. Filtering. The term filtering is used to describe the process of removing a certain band of frequencies from a signal and permitting others to be transmitted. And it talks about the different types of filters, which I've kind of already gone over again in last semester, but this could just be a revision for me as well. Filtering, let's get the definition and then we'll just get the different types. Yep. Then we've got the pass band. We've got the range of frequencies. Okay, so pass band, stop band. So probably just copy and paste this. They're all fairly. So copy and paste it and then remove all of the numbers. Definition. The is known as the pass band. The range not passed as stop band. The boundary between stopping and passing at the cutoff frequency. Filters are classified according to the frequency ranges they transmit or reject. The low pass filter has a high pass band which allows all frequencies from 0 up to some frequency to be transmitted. A high pass filter has a pass band which allows all frequencies from some value up to infinity to be transmitted. Yep. And a pass band filter is in a specific range, right? Yep. A band stop filter stops all frequencies of a particular band from being transmitted. Yep. In all cases, the cutoff frequency is defined as being that at which the output voltage is 70.7 of that in the passband. Don't understand that last bit. But let's put different terms and types of filters. Let's make it normal text and make it bold. Okay. So where are we now? We're at page 97 in the book. The Wheatstone bridge, we've kind of covered that. And we used to convert a resistance change to a voltage change. Yeah, I've covered this last year. So temperature compensation, yeah, it's fine. Problems with signals. Grounding. Okay. So this is an important point. Alright, so we've got grounding. So what I should do is I should look at problems with signals. So grounding. Okay, no, this problem signals like that. I'm just kind of adjusting how I want my notion to look. So generally, the signals from sensors and signal conditioning equipment are transmitted as voltage to the controller. Such voltages are the potential difference between 2 points. If one of the points is earth, then it is said to be a ground signal source. Okay, if neither point is ground, then it's said to be a floating signal source. Ground source of output voltage is potential difference between them. If it's floating source, the signal source is not referred to as any absolute value, and each of the voltage lines may have potential relative to the ground. Okay, so controller such voltage 2 points. Okay, so I don't know. Okay, it's not sure what to write down here, but there's difference in 2 points. Okay, so generally the signals from sensors and signal conditioning equipment are transmitted as voltages to the controller. Such voltages are the potential differences between 2 points. If one of the points is earth, then it's said to be grounded signal source. Okay. If neither point is grounded, then it's said to be a floating signal. Okay. With a grounded source, the voltage output is the potential difference between the signal ground and the positive signal leading source. Yep. If it is a floating source, the signal is not referred to any absolute value, and each of the voltage lines may have potential relative to the ground. Okay, I'm okay with that. When it's just one big chunk of text, I find it actually really hard to understand what's going on. When I break it up like that, that makes way more sense to me. Okay, so differential systems, a differential amplifier, okay, are concerned with the potential difference between two input lines. Okay. Yeah. Okay, I'm right with that. Ground loops from multiple points grounded can be minimized if such as on ground loops. Unfortunately, there may be a potential difference between the two grounding points, and thus significant currents can flow between the grounding points with a low but finite ground resistance. These are termed ground loop currents. Okay. So let's put ground loops. I'm annoyed that how it keeps pasting in and I keep having to adjust it like this. If I paste it into here first, nope. If I paste it into here, yeah. It's annoying that Notion doesn't have a paste. You know, when you can paste in without any formatting. It keeps formatting this in terms of like there's space, there's what enters there, which is annoying. Alright, these are termed ground loop currents, and just put a picture of the ground loop. Didn't really properly. Okay, Electromagnetic interference. Yep. That. So I kind of already have an idea. I mean, most of this stuff I've already kind of studied in last year, so I don't know how much we're gonna go through of this again. But like I said, it's good revision, isn't it? Ugh, it's annoying, man. Pasting this into here. Okay. Okay, that's fine. Power transfer. There are many control system situations when components are interconnected. Thus, with electrical components, we might have a sensor system connected to an amplifier. With a mechanical system, we might have a motor rotating a load. The concern is condition for maximum power transfer between the two elements. Fine. Kind of already covered that. Okay, so now we're on to digital signals, chapter 4. The output from most sensors tend to be in analog form, the size of output being related to the size of the input or analog output from the sensor has to be converted into digital form before it can be used as input. Okay, so digital signals. I can divide it. Okay, so this is talking about the need to sometimes also convert digital into analog. So yeah. Likewise, most actuators operate with analog inputs, and so the digital output from a microprocessor has to be converted into analog form. Yep. Okay. Fine. So let's just put. I just want to get more of analog, digital, and digital, analog. Okay. All right. The binary numbers. Don't need to go into any binary stuff. Are quantizational levels. Quantizational intervals. Don't know what that is. Sampling theorem. ADC samples. So analog to digital converters sample analog signals at regular intervals and convert these values to binary words. Yep. How often should an analog signal be sampled in order to give an output which represents analog signal? Okay, I'm just gonna write this bit here, what ADCs do. ADCs. Oh. Okay, so digital to analog conversion. The input to digital to analog converter is a binary word. The output is an analog signal that represents the weighted sum of the non-zero bits represented by the word. Okay. I intuitively, I kind of understand this stuff, so. Okay, DAX. Simple form of DAC uses summing amplifier to form the weighted sum of all the non-zero bits. Okay, so I'm gonna have to go through and proper study this stuff because I don't really understand how you'd convert a digital signal to analog signal. And I've made a circuit on it on digital electronics, but again, I need to go over all of that myself anyway. So, okay, so ADCs. Input to an ADC is an analog signal, and the output is a binary word that represents the level of the input signal. There are a number of forms of DACs. The commonest being successive approximation, ramp, dual ramp, and flash. So we can put this bit here. Okay. I'm just going through the different types of ADCs. Sample and hold amplifiers. It takes a finite time for an ADC to convert an analog signal to digital, and problems can arise if the analog signal changes during the conversion time. Yep. To overcome this, a sample and hold system is used to sample the analog signal and hold it while the conversion takes place. That's cool. Oops. Yep. Okay. Multiplexers. A multiplexer is a circuit that is able to have inputs of data from a number of sources, and then by selecting an input channel, give an output from just one of them. Yep. This is it's a selector, right? Kind of touched on that last year as well. I knew I'd like this. This is a very interesting book. I'm actually fully looking forward to studying this properly. So, digital multiplexer shows the basic principle of a multiplexer, which can be used to select digital data inputs. For simplicity, only a 2-input channel is shown. Yeah. Okay. The logic level applied to the select input determines which AND gate is enabled so that data input passes through the OR gate output. Which one? Time division multiplexing. Often there is a need for a number of peripheral devices to share the same input-output lines from a microprocessor, so that each peripheral can be supplied with different data. It's necessary to allocate each a particular time slot during which data is transmitted. Okay, this is termed time division multiplexing. Okay. Driving me nuts with copy and paste thing. Okay, there we go. So lines. Okay, so time division multiplexing. Figure A is not time multiplexed, and figure B is. Why is that? B. I don't get that. How is this one even being powered? Or okay, so do these lines here connect to there? That would then make sense to me. So you're going and doing this one, and then going through and doing this. That must be it, right? So, okay, there's their acquisition. So that is used to process or taking. Yeah. Oops. Oh, data acquisition. Okay, so DAC, I'm right with that. Alright, data accuracy. An advantage of digital signal processing is that 2 voltage ranges are used rather than 2 exact voltage levels, distinguishing between the 2 binary states for each bit. Thus, data accuracy is less affected by noise, drift, component tolerances, and other factors causing fluctuations. Okay, so you use voltage ranges to improve data accuracy. Okay. Voltage ranges are used to improve data accuracy. Let's do it in here. Last time. Okay, and then component. Yep, there you go. Okay, parity method for error detection. Movement of digital data from one location to another can result in errors. Receiver not receiving the same signal transmitted by the transmitter as a result of electrical noise in the process. Sometimes the noise pulse may be large enough at some point to alter the logic level of the signal. Yep. So in order to detect such errors, a parity bit is often used. Parity bit is an extra 0 or 1 bit attached to a code group at transmission. In even parity, the value of the bits is chosen so that the total number of ones in the code group, including the parity bit, is an even number. For example, in transmitting. Okay, so that's getting a bit complex, but I can just kind of sum it up, I suppose. Oops. I'll mention it briefly. Transmission errors. Right. Okay. That's good enough for me. Digital signal processing. The term digital signal processing or discrete time signal processing is used for the processing applied to a signal by a microprocessor. Okay, got it. By a microprocessor. Yep. Discrete time signals in that they are not continuous functions. All right, I'm fine with that. All right, so digital signal processing done. Okay, a bunch of maths, and yeah, that's that chapter done. So now digital logic. Don't know how much this chapter gonna take down. All right. So many control systems are concerned. Yep, digital logic. We might, for example, so we might, for example, okay, let's just read this bit. Many control systems are concerned with certain events, emotions, or stopping them when certain conditions are met. For example, with the domestic washing machine, the heater is only switched on when there is water in the drum and it is to the prescribed level. Such control involves digital signals where there are only two possible signals, i.e. on off. Digital circuitry is the basis of digital computers and microprocessor control systems. With digital control, we might, for example, have the water input to the domestic washing machine switched on if we have both the door to the machine closed and a particular time the operation cycle has been reached. Okay. Just talking about combinational logic and sequential logic, which I'm not going to take notes on. Again, AND gate, I've already covered all of that. OR gates, yep. NOT gates, NAND gates, NOR gates, XOR gates, combining gates. This is all done in digital electronics. So there seems to be a lot of crossover, which is nice. So you can just skip through all of this. Sequential logic, flip-flops. I need to go over all my JK flip-flops, D-type flip-flops. There you go. Registers, 555 timer. So this whole chapter here is just digital electronics, which I'm going to cover myself anyways. So chapter 6. So interestingly, we're on chapter 6, and then where are we here? Like, so we've got part 1 introduction, part 2. So we're actually in part 2 of the book. and the book has 6 parts, so we're not really anywhere near through the book. So this is taking me a lot longer. I think it's obviously because I'm recording a video and talking at the same time, so probably looking at 2 times the amount of time for that. Okay, just wondering if I should end this video here and then carry on in the next video from here. I think I'll do that. So yeah, so basically the purpose of this video is, or the purpose of this task really, is just to get a really good idea of what the subject's about. So we're basically, you know, going deeper and deeper into the topic, but without just jumping straight into the book and just studying from chapter 1. I find when you do that, it's very easy to get bored, and also you don't know what's coming next. You don't know why you're learning what you're learning, and it can be super boring to just, you know, sit there and just study, you know, what a phototransistor is and how the how light affects its voltage levels. So having a nicer, broader scope of what it is you're learning, I find really benefits me and keeps me interested in the subject as well. Alright, so I'm going to end this one here, and then in the next video, we'll pick up from chapter 6, and we'll carry on making our way through the book. Cool? Alright guys, thanks for watching, and I'll see you in the next one. Peace.